Yes.
Okay. All right. Hello, everyone. So I'm Flo Davis. I'm an interaction designer and developer at Raymond James. I'm organizer for the Front End Creatives group. It's been quite a while since we've done meetups, but I want to get back to the cadence of at least once a month or twice a month. Harish is also a core organizer of this group, so I didn't want to kind of scare people up with front end creatives, but just kind of it's a mess of design and technology. So we could have things. Some of our past meetups were things we had things on AI. We also had things on design sprints. We had things on architecture. So I've called it front end creative so it could just be flexible when it comes to design and development. But you don't have to be a developer hardcore or a designer or either. You just, if you're interested in like cool topics and more like innovation, that's kind of the things that we're going on here. So, and introducing up next is Harish Biram. So he'll be doing pretty much the speech on intro to quantum computing and anything else he would like to say. So
Yep. Perfect. Thank you so much, Flo. I really appreciate Flo's connection, and it was again through LinkedIn where I met Flo, and I used to work at Raymond James quite a number of years ago, and once I learned that she's also working over there, and then we talked about our interest and passion, and it sounded like we both have a lot of interest on the front end creative side. Uh, so our friendship developed from there, and this topic I was going to give in internally in Agile Thought, where I currently work. And as I was going through the process, and I met Flo, I said, Flo, I have a topic, interesting topic. Would you think your audience will be interested? And she said, sure. And she mentioned as earlier that it's not just front end, it's design, technology, innovation, and this is exactly following in that category. So that being said, my name is Harish Biram. I work at Agile Thought as an enterprise UI UX consultant, and I've been advocating for UI UX accessibility, and also now quantum computing is one of my newfound passion and interest. So today's session of quantum computing, I would like to give you a brief history of it. Like when I got introduced to it, it was always fascinating to understand, but I truly never understood what exactly the fundamentals are. And I know the term sounds uh, lot more trendy, and the term quantum has been really used all over the place now. However, people do not really. Sometimes some companies are naming their companies with quantum, not having to do anything with quantum. So that's one of the challenges that we have to understand, that there could be businesses out there using the word quantum but not having to do anything with it. So my goal today is to help everybody understand some of the basic fundamentals, design, and some of how quantum computing works. So that being said, let's get started with the agenda for today. Introduction. Today's we are going to cover what is quantum computing and a little bit of high level, and then we are going to go a little bit more deeper into quantum versus classical and how classical differs from quantum. Then we are going to see about scaling of classical and how quantum scales. So this is one of the most interesting areas that gives quantum the power because of the scale. Then we are going to look at the three basic fundamental principles and concepts of quantum computing. If you understand these three basic principles, it is going to make so much sense whenever you talk to somebody who is an expert in quantum technology, right? And they understand that you know quantum enough to be able to communicate. So my goal here is to also bring it to the masses. Right now, it's in the It's in the research organizations and some high-end companies, some big multi-billion-dollar companies that are using quantum, or at least researching and figuring the quantum out. However, there are a few talks over there on TEDx or Google. You can search anything. And my effort today was the 20 plus hours of intense learning on quantum made me confident enough that I can share this information, not claiming to be an expert in quantum. That was a different word. Uh, I'm not claiming that I'm an expert in quantum computing, but all I'm saying is I have done this 20 hours of intense learning that can be compressed into this 1.5 hours of information exchange. And in this information that I'll be sharing, it's going to be a lot of breadth and depth, and have an open mind, absorb the information, and do not have to. So it's almost like you have to do a little bit of unlearning, even though we'll do a little bit of comparison. But to understand quantum, one of the challenges that I had was, okay, uh, I think looks like what they are asking me to is completely forget about the perspective that I have about the computers right now, and to start looking at a different perspective of how a computer technology is. Because today, for us, what a computer is, computing is a laptop or a desktop or a server somewhere, or cloud. Even in the cloud, it's a server, right? So, and one server or an array of servers, or like multi machines connected to each other. So that being said, that is our frame set of mindset of what uh, our understanding of PCs and Macs and uh, cloud computing and massive parallel processing, but still on the classical side. However, quantum is a little bit of different, right? That's where we are going to look into these three basic fundamental principles. Then we will look into the advantages and the challenges that quantum brings to the table, because of course there are lots of advantages, and as with anything, there are challenges with it, which kind of are disadvantages. And then I'll share some of the resources that you can now uh, having, if some of the developers are, or if even non-technical people can go and work on quantum, because some of the IBM resources are more user-friendly, so you don't even have to do programming. So you could just use the UI. So uh, that's our agenda for today, which I know is going to be a little bit more. However, if you take it in and research at your own time, feel free to do so. And reach out to me if you have any questions or concerns, even after this presentation is done, through LinkedIn, and I could answer any questions. So that being said, just before going into the first section of quantum computing, I'm going to uh, share this code that has been floating around in this current world of mathematics. So lots of mathematicians and lots of PhD graduates, and there's lots of uh, development have been associated with mathematics, which is great. Uh, However, mathematics has been, I have no objections where it has been revered as the language of God. So what they are saying is mathematics is the language with the God has written the universe. That's how there is a saying, and you just Google this out and you will see so many quotes, right? I just wanted to advance this a little bit, and this is what I am thinking. And this term is not. Let's let's take it to the next level. And in the next level, it's quantumatics, and this word doesn't exist. And this is my coining of the term quantumatics. Quantumatics, and I will go into the later detail what it is. Quantumatics is the programming language with which God plus humans have been writing the multiverse. And if you do not believe in the multiverse, that's fine. If you believe in two galaxies, then that is also a belief. So then multiverse is also a huge topic of debate, right from MIT, Stanford's, Harvard's, and lots of papers in multiverse and those kind of things. So this is just the code upgrade. So the code from mathematics has been upgraded in my mind to quantumatics is the programming language with which God plus humans have been writing in the multiverse. So the what I say is mathematics is helpful from understanding from A to B. I want to know how to go from A to B. That's where mathematics comes into the picture. It's almost like I want to go from Florida to Georgia or Tampa to Georgia. Then I can take a bike and I can ride for a few days. Then I will be able to get there. Or however, quantumatics, which I've been saying, is A to B. You would not use, which is from Florida to Atlanta. You are not going to use quantumatics, which is this level of rocket, rocket, which also is a vehicle. And in the terminology, these are two vehicles. One vehicle is letting a person go from A to B on the ground level in a single direction, single most direction possible, so that the person can get to A to B. And quantumatics is also letting people go from A to B, but that B is far off distances, not Florida to Tampa to Atlanta. It's Tampa to the Mars or Tampa to the moon, right? And and with the technology in future, maybe we'll be going to far off planets as well. But that that has to be we have to wait and see how it goes. So in my mind, what quantumatics is a combination of quantum computing, mathematics, science, research, technology, design, innovation, architecture, biology, engineering, solving the computational solving of challenges, right, and multidimensional. And then it's also intuition, thinking, and feeling. So this is one of the things where mathematics. This is why I was saying mathematics will be only one thing, uh, whereas quantumatics is a combination of plus this, plus this, plus this, plus this, plus. Because until now we have been on silos. Mathematics research goes on its own, whereas technology research or innovation goes on its own. But quantumatics is going to be there. So those were my philosophies and a few 2 cents to quantum computers, which I really would like to write an article and in future and uh, just give a little bit of awareness to people. That being said, let's look at what is quantum computing. You might have heard about this quantum computing a lot in the past, but you might have not had a chance to look into it. But this 1 hour is going to be so much information that it's almost a time compression in my mind. So whatever it took for a passionate human being to learn in 20 hours can be transferred in a nutshell in this time compression of 1 hour. And if there are 20 people on this call can benefit. So that is 20 multiplied by 20 hours is 400 hours of learning in the human beings, right? But if we compress that from 20 hours to 1 hour and then share it, then people can start learning on their own. So that it's efficiency to the mankind that we could learn and share and collaborate and help each other out by sharing more and more information and knowledge and expertise and experiences. So in that, the quantum computing has been evolved from quantum mechanics, But in quantum mechanics, it's basically it's a strange ability of subatomic particles, right? Subatomic particles being electrons, protons, neutrons, electron cloud, and all of that stuff. Subatomic particles um, to exist in more than one state simultaneously at any time, right? So a particle is existing into multiple states at the same time. So this is very challenging to understand because it it is almost like the frequency and the vibration of these subatomic particles, which, when looked closely, are more like a wave, not a wave function, or like a cloud, not an absolute particle that you can get hold of. I mean, you probably can get hold of, but they are at the higher frequencies. So that being said, it is very in these subatomic particles, this is where a lot of research is going on in the technology with Large Hadron Colliders to go into the subatomic particles to be able to understand even into the subatomic particles like what exists, right? And that is where there is so much challenges to be able to create those environments and to be able to measure them in such a milliseconds. I think it's milliseconds or microseconds. That's how much the state holds on to. So it is the strange ability of subatomic particles to exist in more than one state simultaneously. So it could exist in multiple states like that. So this is probably the way the particles behave in the subatomic, and that's why it used to be called as electrons before. When I was in the school 20 years ago, it used to be called electron proton, and then they started saying it's electron cloud, proton cloud, and it's not a particle, it's a wave function. Let's not fool ourselves saying that everything is absolute, everything is a particle itself. So this is one of the changes that the paradigm shifts, that the scientists have to agree that something can exist in a cloud fashion, and but it is still a particle that's at such a high vibration and frequencies. So this is the way the particles behave, right? So you can uh, when you see it, it's almost like a vibration, and then it's completely going very fast, right? Until that. So what quantum computing in terms of performance offers is a high level of computational only with a few error states. So the error state should be as low as possible, and these qubits can go into um, higher computation power. But if you have a high error rates, the computation could not be so easily achieved. So with so it's almost you are better off using a classical computer than using a quantum computer at that particular point. So we are going to get into more details of what a qubit is and all this. Just for now, let's remember that uh, quantum computing operations can be done in much more quickly. And that is the scale of magnificent scale that it offers. And one of the basic uh, uh, features also is it uses less energy. When you are using hundreds of thousands of computers, and when you can use one computer, one quantum computer instead, this is going to save a lot of electrical energy, electromagnetic energy. There's so much energy transfer, right? Electricity, and lots of data transfer. So there's huge amount of savings when quantum computers are going to be mainstream media. Uh, right now, it is not a mainstream media, but it is going to be such a huge energy saved. As you can see, classical computing has to exponentially grow to meet the same need. So quantum computers could have just done with these many bits of computing, and these as you go to this bit, you are saving this much amount of energy. So if energy is on the y-axis, and x-axis is where quantum bits are, so computations. So you could see how slowly and linearly quantum can will use the energy, whereas classical will be just consuming the energy to the next level. Like it's and it is more taxing. It's very taxing on classical computers. So it does not look like quantum computers does not look like your PCs, your laptops or desktops. So it looks like there's a hugely vacuum and uh, very cold, uh, absolute zero temperatures, like very, 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 very cold temperatures, and maintaining the uh, particles at this state. So, so once you keep all these refrigerants and uh, uh, keep all these machine running with the coolants and producing the environment, then the particles are raising to the quantum state. So until then, the particles will be not in the quantum state, and then you can, the particles can be, when they are in the quantum state, they behave much more differently. So in the classical, if you see the background of here, the classical can just go into one direction, come back, or go into one direction, or even in parallel processing, what we say, parallel processing can happen in the classical. Yes, it does parallel processing, but it still is going in one direction. Whereas in the quantum, as you say, quantum is going in multiple directions and reaching the endpoint more faster than the classical one. But let's look at the chips and the bits, right? So this is our classical chipset, Intel or whatever, AMD chips, whatever it is, right? Microprocessing chips. So what they do is they are very good as computation, and they take a lot of instructions, information, and then they do all the computations that are needed. So even right now, when what we are doing with this virtual Zoom call on this session, we are using classical computers, and this classical computers are sharing the bits and information uh, via the wires, which is your internet, and it's transferred so fast that um, because all of our PCs nowadays are PCs and mobile phones are much more computationally capable versus 20 years ago or 30 years ago where the computation was. So that's why we are able to do live streaming, live videos, and we are able to share information almost like instantaneous real-time basis. So which is great. See, and that is actually, quantum is not going to solve that problem of real-time videos, audios, images. Classical is great, and classical will continue with that. Do not think that quantum computer will allow you to do better quality of videos. We are already having high definition video quality streaming, right? Sometimes the quality is so better that in the real time when you see somebody's face versus somebody's face on the TV, which is high definition, and the relay is on high definition, that's even magnified and zoomed versus the real face is only uh, X number of inches tall or X number of inches wide. So this is one thing I wanted to make crystal clear, that videos and audios and all this stuff is 100% going to be always on classical computing or next generation of classical computing that comes on board. But quantum computing is not going to replace that. So it takes the instructions, classical bits, and it does the computations necessary for it. So classical bits, and it's like a fundamental unit. As you can see, we talked about the instructions, right? And the instructions and the computations that needs to be done has to be done in bits. And in the bits, in the classical, either it is on or it is off. It cannot be on and off at the same time. So an analogy is this radio toggle, right? You cannot say it's on and off at the same time. Either it's on or it's off. And we'll have a better light switch analogy later, but just thinking this. And then to have both on and off at the same time, you need two bits. This bit holds one state, and this bit holds another state, off state. So 0 is for the off state, on for the one state. But to have anything working, so as an on and off state, you would have to hold information in two bits, 0 and 1, 0 and 1, 0 and 1. So this is kind of limiting for the classical computers to work like quantum computers, right? So that's why the whole architecture and the whole engineering and ingenuity innovation had to move away from bits of the classical bits. And once quantum mechanics was introduced, people and researchers started seeing the power of that and how to create something called qubits. So quantum chips, as you might not have seen, this one you might have seen before, this chipset, and you might not have seen quantum chips. And there's quantum bits, qubits. And qubits could be anything. And nowadays, people are doing cryogenic qubits, or they are also trying to make a qubit look like a chipset. There's so many researchers all over the world jumping on it and doing so much great work. Trial and errors are happening. So what is quantum chipset helpful for? Exponential computation. It's going to help you with taking the exponential computation that a classical computer has, as you have seen in the previous slide, where classical was going as an exponential level and quantum was not even stressing much. It just is going at a linear scale. So that's where you can see the classical versus computational power of quantum computing. It uses less chips for the computation, and it can do more computation. A qubit can take any state at any point of time. That means an off state, on state at the same time. So that's both 0 and 1 at the same time. So remember the qubit, classical bit was on or off. Remember that scenario. And now it's on and off at the same time. It's just, you have to figure it out. There's another term called measurement that we'll talk at the later stage. That's going to help the qubit. Next. So it uses 0 and 1 for bits, 0 and 1 at the same time. So a classical bit versus quantum bit, right? So 0 and 1, two different distinct states, completely separated each other. And this is like two intermixed all together at one, both at the same time. So when we want to see what the actual classical computing power and the scaling versus the computational scaling with the bits, and we need to start understanding, before we understand the exponential level, and yeah, this is the end state of how exponentially classical computing goes exponentially higher. However, quantum computing is just going very thin, linear, very modest increase, right? But because these particles are different versus these particles, and the information from these particles that are getting exchanged and the data getting transferred is much instantaneous and much faster in computation as well. And more computations can be done, right? So that's what we talk. And we are going to look into more first from the granular level, and then we'll build up into the computational level. So classical bit, we know bit is on or off. Then in the quantum chipset, quantum bits, it's both on and off at the same time. So now these are side by side. We can see what the difference is. It's almost like on and off these two buttons, but the decision of which one will be made when it's done measurement. So which we are going to cover later. But just for now, if you can simply accept that it is both 0 and 1 at the same time. And I will try to demonstrate with more analogies and examples as possible so that we can understand it a bit more detailed, clearer. So qubit, 0 and 1 same time, bit 0, 1 time, 1, 1 time. So classical, this is the light switch analogy that I mentioned earlier. When we take a classical switch or like traditional switches that we have at our homes, it's either on or off. If we want to show on or off at the same time, then you would have to have two switches, on and off switch. However, quantum works like the dimmer. The switch is still on or off at the same time, and it's your decision. You do not need two switches to do on or off at the same time. I'll let that sink in. Uh, you do not need to have two switches like here to have on or off at the same time. You can just do with one switch because it can go to on and off at the same time, and that's how a qubit kind of functions. So scaling a classical computer, right, in this we will start looking at the permutations. So now we talked about the uh, one bit uh, one bit or two bit classical and then quantum and qubit and two classical bits, and classical bits are 2 bits related to 1 qubit. So there is a formula, and that formula is, so the permutations, so one possible permutation on or off is one possible permutation. So one permutation and two. So there are two permutations or two states for one permutation. So let me try to be more clear here. One permutation is state of 0 and a state of 1. So if you use two switches, right? Right now, if you want to have on and off at the same time, you have to have two switches, two classical bits, and then that is going to help with the states, which state it is on. But when you come to the quantum side, with 2 qubits, it can, because it has not decided what bit at what point, but when you ask it for a decision, when the measurement happens, it can decide, okay, both of them are off. It can decide with the permutations of 2 power n. And 2 power n is all possible permutations. And n is equal to the number of qubits. So the number of qubits is 2. So 2 power 2 is 4 possible permutations. So right now, the permutation 1 is both switches are off in here, like both switches are off. One switch is off and one switch is on. Like the first switch is off and the second switch is on. Like this first switch is off, second switch is on. So this is showing this permutation. And then the third one is the first switch is on and that's second switch is off. So if you imagine the opposite sides of it, that's the third permutation. And the fourth permutation is both switches are on, and then you could see that it is 1 and 1 for on state. So 1, 2, 3, 4 permutations, and So here I would like to just clarify, with these four permutations, you have multiple states, right? So the four permutations is almost like a row level. So row one, row two, row three, row four. Those are four rows and four permutations. And states are individual level. State of zero is state one, state two, state three, state four, state five, six, seven, and eight. So now there are eight states that are happening here for this. Whereas, and when you see the possible permutations, and this could have only one state at a time versus multiple states at a time, and how it can exponentially calculate the permutations, and this is calculating one possible permutation. So let's look a little bit more closer to it. So what's happening here is one possible computation is having 0 and 1, and one permutation, two states. And in quantum, we have, as we said, n is equal to 2. So this is the switch 1, and this is the switch 2. So the switch 1, 0 and 0, off and off, and switch 2, off and on and off, and then off and on and on. So what you could do with these two switches, with two classical bits, if you use two quantum bits, you could do these many four permutations, which is 8 states. If anybody has any question, let me know. But if not, we can also ask questions at the end of this session. So that's pretty much it over here for multiple states and multiple permutations. So when we start doing a little bit of simple mathematics, very simple. 2 power n, which is 2 power 1 for 1 qubit, is equal to 2 power 1 is 2 into 1, and then 2 permutation, right? And 2 qubits, 2 power n, is 2 power 2. 2 multiplied by 2 is 4 permutations, which you just saw in the screen earlier. Then 3 qubits takes you into 2 power 3, and 2 power 3 is 2 multiplied by 2 multiplied by 2, which is 8 permutations. 4 qubits, 2 power 4, which is 16 permutations. So, and now in the next slide, you would see the states. So it is the permutations, and one qubit could have two states at one time, and one bit has one state at one time, right? We talked about this. And the P is for permutations, and N is for numbers, and S is for states. So one qubit is 2 power n, which is 2 multiplied, and 2, that is 2 permutations, and 2 permutations multiplied by 2 states, that's equal to 4 states, because they can hold 1 and 0 at the same time, and that can give 4 states. So P is still the permutations, and one qubit. Actually, qubit is QUBIT, but I just left out U here, so I'm just saying qubit. One qubit is equal to 2 permutations, and then multiplied by 4 states is equal to 8 states. And then 2 qubits is 4 permutations multiplied by 4 states, 16 states total. 3 qubits, 8 permutations multiplied by 4 will give you 32 states. And 4 qubits will give you 64 states. So how does it look like, right? So we took the analogy of, we kind of saw this earlier, 1 qubit, 2 permutations, and 8 states. So these two are able to have 1, 2, 3, 4, 5, 6, 7, 8 states, and we looked at this earlier as well. So, but two of them are able to do this many states with just two. So if we scale that, 2 power n is for 4 qubits. How many states can you solve in the classical? So 4 qubits can solve classical bits of 64 states, on and off, on and off, and we saw that number in the previous slide, right? So this the this before we move to the next slide. So I just wanted to give uh, this connection in the mind. So 4 qubits and 64 states, 64 classical bit states was the calculation of 4 qubits, 64 states. And now you do multiply by 2 power 5, it's going to go like that: 2 power 5, 2 power 8, 10, 20, 30, 40, 50, 60, 100, 200, 300. So this is one of the numbers of how much computations can happen. So the actual rounded number, this is the rounded number by followed by 90 zeros. Uh, 90 or 91 zeros is 2 followed by 90 zeros. So it's a 91 digit number. So how many it's a very, very large number. I can't even say this. I mean, trillions and trillions and trillions and trillions and trillions of computation. And that is where the power of quantum computing comes, right? And if we have 300 quantum bits, nothing in the world that exists at this point can do 300 quantum bits, qubits. The maximum is 75 or something. Google or IBM, those guys are having it over there. But now imagine the power of quantum bit that is quantum bits that is 300. It is equal, it's beyond the number of all particles in the universe, in the known universe. So in the known universe, the anticipation is 2 to the power of 64 or 2 to the power of 272 is the number of particles. That's each and every particle on the earth, on the solar system, on everything. So this number seems low, that so that it, since we have written it down on the paper or on the PowerPoint slide, it feels, oh, it's not such a big number. But when you start counting these numbers, it you would have finished all the earth, solar system, galaxy, and almost finished the universe, counting all the particles. And so imagine how much computation states, and those are the states of uh, computation, and the states and the permutations that it can deliver if we have 2 to the power of 300 quantum bits, which is exponential. These many, so 300 quantum bits will be equal to the states of these many states of classical bits. So you need these many classical. So that means if we needed to do anything higher level of computation, we have reached the maximum of classical computing. You cannot um, increase the speed any further, because going to Mars doesn't happen with a bike. I mean, you can't even go from, excuse me, you can't even go from country A to country B, which has water in between, with a bike, right? So you have to come with a different tool or a different technology. That's why you have boats, or you have to fly. And that's the limitation of classical. To do higher level of computation, you cannot just keep on adding more and more computers together and ask it to do faster processing. It's not going to work like that. Excuse me. So linears versus mass parallel states, right? So the linear state is this with the classical bit, whereas a qubit is up. Q, linear state is either blue or this pink for 0 and 1, and the quantum state is blue and pink at the same time. And imagine this ball rotating at a very, very, very high speed. Uh, and you don't know if it is going to be taking the if you're going to get, so if you see more sides of it, let's say, I'm just trying to give an analogy. If you try to see more of the blue, then you can say it is off. If you see more of the pink, then you will say it is on. So right now it is more on the off side, but the measurements will tell. So we talked about the particle and the wave function, and it's uh, and the classical bits. The challenge is because of classical bits, the bit numbers and everything. They work like a wave or particle function moving from A to B, A to B, A to B, and it's like an object that moves from here and there. But that object is not rotating, that not vibrating at a frequency, at an energy, and at the vibration that cannot be, it cannot be instantaneously at another side. But with the quantum, the particle is instantaneously on any side wherever it decides to be going to, because it's almost like a wave function. Here is a great analogy I found that probably is going to make more sense. So if I take a measurement, like take a snapshot of it, at this point, it's zero. At this point, it's one. At this point, it's zero. At this point, it's one. So what I am measuring at, right? So imagine this cylinder as one and this hollow cylinder has zero, right? So if we need to get a, so imagine this moving at a huge speeds that you cannot even imagine, and then you took a snapshot of it. So as soon as we take a snapshot, let's say it was that, yeah, it was that, then it is zero in the classical bit. But if it was like this, it's one, and it's always in this limbo state. So it's always that gray area, and we have this as human beings. Sometimes you're not sure. One of your friends, colleagues, family members, spouses, kids, somebody's asking, "Are you coming to the event or not?" Right? Are you coming here or not? Are we going or not? They want a yes or no answer, and you haven't decided. Truthfully, you are not on the edge. You are on the edge. You can be convinced to go. You can be convinced not to go, and your decision is in that gray area. So this is that gray area. So, and you say, hey, we have time, we will decide just before the event, right? So let's say it was a birthday party of the kids, birthday party, one of the friends, but and they wanted to go. You wanted to go maintain the social distancing, but you at the same time you want to be careful, right? It's a decision that you want to delay until the time has come, very much. So even if it's a virtual, you probably would have no problem. But if it's a physical going there, maybe it is you want to check what the host is trying to do, right? So it's like that. Quantum is like that, where a decision is not made until the measurement is done. So when you try, so I'm just trying to give another analogy with quantum. If you try to play chess with quantum versus playing chess with uh, classical classical, there are people in the world who can beat chess with the computer, with the highest form of its performance. There are there are people who can beat them in chess, and with quantum you cannot. There is no way you are. There's like 70, 97 with classical. You will have 53 to or 50, 60% chances that a highly like Vishwanathan Anand or Gary Kasparov or some of the highest chess players, they have chances, right? They have 40% chances, and classical will have 60% chances. With the quantum, they have zero chances. because the quantum will have 93% chances, and the 93% is only because 3% are failure rates. We looked at failure rates, or like error rates, and quantum, to win against quantum with the mm, human mind, it's highly improbable, because it had already calculated all those states before you have. So it it is much more. It's so if chess is becoming a little bit of challenging to understand, let me go and give another analogy. Let's say you are playing heads and tails with and you bet with the quantum, that and you are closing, you're tossing the coin, and you're closing with the heads, and you are taking a position of heads, and you're asking the quantum to take the position of tails. Because you took heads, it will take tails, right? With the classical, there are again 53 to 60% chances the classical will win, and you will lose 40% with the classical. So you have still 40% chances of winning with classical. But with the quantum, you have zero chance. It's 97% it will win, 3% you will miss catching it at the right time. That means you are not catching the coin at the right time. It fell 3 times, but 97%, which is when you caught it correctly, it is winning. That's the power of computation at the massive scale of, because the information is so easily computed versus, you know. So we looked at something like this, right? So qubits, almost these many, very, very qubits, 30, 20 qubits at this point can perform the permutations. So, and these permutations, so 20 qubits can easily perform these many permutations, whereas classical, it will take a lot more permutations, a lot more qubits, lots more classical bits. So I've been talking about the three basic principles or fundamentals of quantum computing, right? And when we talked in the agenda, and I've been saying one of the, because I couldn't talk without kind of revealing quantum measurement up front, because that is one of the principles. So these are the three basic principles of quantum computing. A, it's quantum superposition. B, quantum entanglement. C, quantum measurement. And this is the one that I've been saying upfront, that the measurement, until we do the measurement, the quantum is going to, you cannot tell which state it's going to take. It's going to be on or off. You have to do measurement. So let's look at the A, quantum superposition. So the superposition is almost like you can think of these two uh, balls inside of each other, or overlaying of each other and rotating at a higher speed, right? So it's like when it points to the north, then you will say plus half, and when it points to the south, you're saying plus half. So it's very difficult to imagine two things inside of each other. So let's for the sake of imagining, we have to separate it out, right? So it's moving, and then when we catch it pointing to the north, then we give it plus half points. When we catch it pointing to the south, we give it minus half, right? Or south and north in this direction. So this is the definition from the internet, or Wikipedia, or whatever it is. So it's the quantum state. What quantum superposition is nothing but it's the quantum state where particles can exist in multiple states at the same time, and which allows quantum computers to look at many different variables at the same time. So, and this is one of the reasons why we mentioned about chess. Chess, you have to look at many different variables at the same time. So, whereas human brain can do that quantum computation, but we have evolved linearly. Our brain, some it it's like you. And another analogy I would like to give, because the more analogies we get, the better we can understand it. Imagine you are looking at TV. One TV you are looking at, that's fine. You can easily grasp the information, you can tell. You can put two TVs in front of you, you can still tell. You can put three TVs, it's going to be challenging to tell what's happening on each TVs with the sound, right? With all that. And imagine a room full of 1,000 TVs, and now you are trying to figure out what's happening in these 1,000 TVs. Everything is playing different channels. Everything is playing one channel. Yes, you can easily compete with quantum. If all those 1,000 TVs are playing one channel, and you are watching the 1,000 with the same frequency, one channel, then it is, yeah, you and quantum will be at the equal. But when it comes to 1,000 different channels, and you are watching the 1,000 different channels with your brain and eyes and trying to figure out what is going on where, quantum has can use those different variables, 1,000 different variables, and it can exactly calculate, and it can exactly tell what happened in each channel, versus you seeing a channel, figuring out so in that you might look at three or four channels at the max and say what exactly happened in these three or four channels while you were looking for 5 minutes. And quantum can tell everything without having to, because it can calculate those variables. And this is just an analogy, right? So how it's probably, you might have known this movie called Golden Eye, or Eagle Eye, or I think Golden Eye, something where Ethan Shaw, who has a high IQ and is working with the secret Golden Eye. I don't know. If I'm trying to Golden Eye, I think. Yeah. So in that eye, if you remember that, he enters into the building, and the eye welcomes Golden Eye or something. Yeah, it welcomes, and it says his name. It says and everything. It is like, and this person is just wondering like, wow, this guy, this quantum computer, this Eagle Eye, Golden Eye knows me more, or more about me, uh, all that, right? So it's almost like that. It has that much of computational power to make sure everything is so. So this is, if as I was saying, when we measure it, we can tell where it is. So it's going with this frequency, and when it is measured in this, it was somewhere around here or something. So it has to decide it's at zero state or it's at one state. And if it is somewhere here, it has one state. So we have to. So until the measurement is done, it's just not possible to tell which state it is. Is it at zero state or one state? So that it's very much needed for a measurement. And this is the superposition, right? Where you could see two things at once. So that's the measurement, and this is the superposition where you see him twice, right? Where you see him for a bit of a second. So that's how the superposition is. And it's zero, and it's zero and one at the same time. So one other way to figure out what quantum state is, and it's moving at a higher frequency. And then once you measure, once something of a measurement is happening, microscope or whatever it is, then it takes a position of a state. So classical, you can easily tell on and off, and quantum you cannot. It will be both on and off at the same time. And these are the classical states. with the superposition, and with quantum, it's a quantum state with this superposition. So here is an example how a maze is solved by a classical computer. It goes one direction at one point and it's trying to figure out, okay, let me know. Even though there's parallel processing, it can do that, but it's going to take more computers. But this is how fast the quantum can. This is the. I wanted you to look at the classic a little bit more, how much time it has taken to calculate. And now we'll go to quantum and how it is going in different variables at the same time. That's it. So if this takes like 7-8 seconds, the other one was taking 21 seconds. So how it doesn't, if you remember how the previous one was coming back and then going in a different, the black are like figuring out a different path back. So all this wasted cycles, say wasted states, it had to be done because it couldn't figure out. It had to go there, figure out, and then come back. Whereas here, there is hardly any wastage. It knows to send four or five different variables and then just start computation on those variables, and one of the variable will yield the result. So one variable will come out of here. So nothing is wasted. Time is saved. It's much more efficient. So that's quantum superposition. This is very interesting topic of entanglement. What's called quantum entanglement? I mean, this is just do the physical definitions before we go to some pictures and slides. So physical phenomenon that occurs when a pair or a group of particles is generated. When a pair or group of particles is either generated, interact, and share special proximity. It's in such a way that the quantum state of each particle of the pair cannot be described independently of the state of the others, even when the particles are separated by a large distance. I think it's a difficult concept to understand, but I would like to try to give analogies to understand more. Classical is almost like a remote, not having a remote. You are going to the TV and manually switching on and off. But with the remote control, you don't even have to be closer to the TV. You can switch it on from here. So quantum works similar fashion. When a particle is entangled, it's called quantum entanglement. They share the information. They interact with each other, even with the spatial proximity. That means if a particle over here on Earth is entangled with a particle in somewhere in Andromeda galaxy, they share the information. So that means if if as a person, if we assume there is other living beings in Andromeda galaxy, and I have a quantum entanglement with one of the being over in the Andromeda galaxy, and I being in Earth, away light years apart, but we have quantum entanglement. Our frequencies and our vibrations and our energies, uh, everything are with in such a phenomenon that we are sharing the information. That means the person in the Andromeda galaxy doesn't have to be, not even have to call me, tell me anything. The information is just shared instantaneously. So this this makes me wonder that the way human development has happened is being helped by other species. That's where we talk about UFO, unidentified foreign objects, and other stuff. But I think what they are trying to do is sharing the information so that we can benefit with the technology and we can help the human race and the mankind move to the next level of evolution. So, so quantum state is something like that where you do not have to be physically close to each other to share the information. Um, to to put it in this perspective of I can call my mom in India and I can talk to her and share the information, but at least I'm sharing, I'm taking a phone, I'm calling her, and she's having to lift the phone and sharing. But with this quantum entangled state with my mom, if I can just share, hey mom, how are you doing? Are you doing okay with the COVID? And and imagine this is in, it's not even in the dream, in the real time. This is happening where my mom says, hey, don't worry, son, I'm doing good. We are keeping safe. But everything happened through one entangled particle with me and my mom, probably in my brain. So if my brain has entanglement with my mom's brain to one particle, then we can share the information. I mean, this is again hypothetical uh, saying. What the the potential of quantum entanglement is what I'm trying to explain in such a way that how quantum mechanics, and quantum computing works. Because to this date, they know uh, the entanglement is possible, the superposition and the measurement is done, but scientists doesn't know how it works, right? It's almost equivalent to anesthesia. To this day, we have been using anesthesia for a long time for doing operations and surgeries. However, nobody has a clue how it knocks out the consciousness and brings back the consciousness at an X amount of time. We know how to use it. We don't know how it works internally. So, quantum entanglement particles, it's almost like from this universe to this universe. When these particles are entangled, they can share the information and you can instantly get the download or upload to these particles. And it could be at much higher distances. And once they are in that distance, so being in on the earth versus anywhere in the universe or multiverse, you could just share the data can be shared. Uh, so that's the power of quantum, but on our current level of human development and mankind where it is, it can only relay this information for 100 miles, 100 miles or because the quantum loses the state. And after that 100 miles, then it has to relay that information and 100 miles. So that being said, that's one of the very big challenges of the current quantum technology. So when it is, the concept is when it is entangled, the information can be shared. It could be anywhere in the world, in the universe or multiverse, but the instantaneous sharing of the data can happen. So quantum measurement, the snapshot of quantum measurement. So this is what scientists have done, a snapshot, and this is like measuring a quantum measurement inside of a lab or somewhere. When these particles are highly charged and they are excited, the quantum state is to excite a particle to that state. And if that particle doesn't get excited, then it's regular, like a classical bit. But the quantum bits, if you excite them, they vibrate as a higher frequency energy and uh, uh, vibration, that it will be in an extreme excited state, and that state is only for a few seconds. So that excitement has to be kept on going, and then when it is excited, then you need to catch it or measure it. So what's quantum measurement, right? So to become a qubit quantum state bit, right, a classical bit, or when a classical bit has been excited to a level, such higher frequencies, then it will achieve quantum state. But when the quantum state lowers down, then the quantum state will collapse and become a classical back. So this is again the textbook definitions of internet definitions. A system remains in its superposition state, right? Unless it is measured. So once you start measuring it, it loses its superpositioning state. A quantum bit, and this is the slit double slit experiment. If you look at double slit experiment, when they've fired particles across one slit and two slits, and there's good YouTube videos on double slit experiment when particles behave on a quantum state where it is wave function and rather than a particle. So a qubit or superimposed quantum state formed by a linear, like this kind of measurement where the calculations are going, it becomes a quantum bit at certain state, and after that it becomes after it loses, so environment has to be kept like that, and then once the measurement is done, it loses the state. So QC built, so quantum computing built to run specific algorithms. So uh, this is one of the challenges, right? So there are different algorithms like Groover algorithm, Shor algorithm. These are two better known algorithms, right? The computer, the quantum computer, has to be built and rebuilt based on the algorithm that it needs to run. This, yeah, because we are in like a quantum, very early stages of quantum, almost like infancy stages of quantum. You would, it's almost like asking your classical computer, which is your computer, if you want to use Microsoft Word, you have to uh, rebuild your computer, and if you have to do Office PowerPoint, you have to do another rebuilding of the computer. Then this is such a challenging to come to the masses. That's why it is not in the masses. It's only in the very research R&D laboratories, big companies, IBM, Google's, and those of the time. And countries are also investing in quantum too. So uh, different algorithms, you have to rebuild the machine. So that's one of the big challenges as well. So there are multiple algorithms. If you're interested, you can look at these algorithms. But there are specific purpose algorithms, right? And then the ones that are the Groover's algorithm, it helps with the unstructured databases. It can quickly search. So it's almost like it can search the entire Google with or index, or I don't know if it can index, but it can search all the Google databases more faster than what, or all the internet information, which is unstructured databases, in much more faster than Google does right now. So, and the Shor's algorithm is to find the prime factors and those kind of computationally heavy mathematics. Those are the ones that can be done with Shor's algorithm. So once a stable quantum computer gets developed, except uh, that machine learning, like it will accelerate. Like what we are doing, machine learning and artificial intelligence right now, it's going to be exponentially higher. It's going to be much, much more faster, and this gets to a way that the YouTube or the Google or anything, Facebook, Twitter, and they could instantly, like, not, I don't want to say instantly, but at least in few seconds, once you posted something on your Facebook, so Google can instantly know that, and it will say, hey, would you like to post it on YouTube too? Uh, because we see that you would like you. Let's say I post this one on YouTube or Facebook, and then uh, Google guys can email me in few seconds and say, would you want me to post that for you immediately on YouTube? And just click a button and say yes or no, and that's it. So you don't even, that's how much they are going to be able to do that instant sharing, instant near real time information exchange. All of that could be possible once it is mainstream or high developed. So this is one of the things that the cybersecurity world really pats their back on themselves, that they have RSA's to 2048 encryption that takes, it will take billion years for a classic computer to break that encryption, and a quantum computer could crack it encryption in seconds. So let's say if you have a 2 to the power of 300, that is 300 qubits computer, and you give that encryption challenge to this versus that. So 300 classical bits, or you can take 3000 or 30, whatever, and then you could ask it to calculate versus here. So this is one of the risks that cybersecurity world knows, and hence they are developing a much more quantum encryption, quantum level security encryptions, because this this classical thing could be easily broken by quantum. That's one of the sayings that is there. So, and then the IBM's yeah Deep Blue uh, defeated the chess champion Gary Kasparov, right? So in if it was able to gain the competitive advantage, right, because it examined 200 million, so the 200 million possible moves each second. So if you can imagine 200 million possible moves, and how many possible moves can a human brain do? X number, right? And a quantum machine would be able to calculate 1 trillion moves per second. So this 200 million was with a classical computer, IBM computer, right? And with the quantum, 1 trillion moves. So human being has no chance to, I mean, like, this, the level of intelligence that the quantum, I would say it's quantum intelligence. It's no longer artificial intelligence. Artificial intelligence is what we are talking about. The classical arena that we have right now is AI. Yes, it is AI. But when you come to quantum intelligence, this is human beings. It is much more bigger than human beings' capability of, at least uh, not one to one. You cannot compete one person to one person in quantum, one quantum computer. A group of human beings, a mass of human beings probably can compete, but quantum is here to help, not to hurt, not to say that human beings are artificial beings, or like are sorry, human beings are not capable of its level of intelligence. It is not trying to prove that. It is trying to say that, hey, leverage my computation skills. It's, and I will do the work for you. You can focus on creativity, ingenuity, innovation, designing, architecture, engineering, medical sciences, biology. So why quantum is evolving, I believe, is to help the mankind to go to the next level rather than doing all these computations, trying to figure out all this work for so many individuals. It is going to be challenging. So this is one other challenge, right? Coherence and bit. If they are in the coherence, how long can so it's like they have something called interference, and if the interference is too much, it will lose the quantum state, right? Uh, I think it's better to, and this is more like the challenges that they have. If there is interference, like it, because it is at the extreme vibrations, extreme frequency, extreme energy, uh, it's very sensitive to any interference. And as soon as the interference comes, it goes, it dies down to the normal state. So to achieve the stable state, the computer platforms require vacuum setups, right? And then those have to be superconductivity there, and then they have to be super cool, absolute zero turn requires cryogenic cooling, right? And that cryogenic cooling, huge refrigeration. We saw this example in the beginning, and extreme low temperatures. So as we just briefly mentioned about quantum's benefit versus this, imagine this world's tallest building that's in France. If world's tallest bridge, not the building, which has been built in France. It took a lot of years and a lot of engineering, architecture, and the architect was amazing. The way he drew this, these are two pillars facing each other, but they are hollow. So it looks like this, but there is a hollow gap on one of the side, and it looks beautiful from another angle. So, and if you can see, this is one of the, and sometimes the clouds goes below the bridge. So it's at 350 feet high or something, incredibly high feet, and then it's incredibly long, 7 miles or 8 miles, or 7 kilometers or something. To build something like this, can you imagine one person building it, or one team, like 8 people, 10 people building it, right? No, it cannot be happening with 8 people building it. It will take a long time to build it. So they had a combination of companies, multiple people, multiple things happening at the same time, parallel processing, um, all that stuff. So while these pillars were going, these were getting built, and then they had so much challenges to touch each other, and then they overcame. And there is a YouTube article on this if you would like to one day for time pass, how challenging it was to build this. But it was only possible with the teamwork and with the combination of multiple companies, multiple people, multiple teams. And they were like 7 teams, 1, 2, 3, 4, 5, 6, 7. All the seven were done by 7 different teams building each pillar. And then other teams were building on this and that, and then trying to join. It feels like it's simple enough, but as you see, this bridge was not simple. This was an engineering miracle and an architecture miracle, a civil engineering miracle. Uh, but it took some days and some years to build it, and some very, very big challenges to overcome. So why I'm telling this right now is this quantum is such a level. It is, let's every it's not about the country, it's not about the company, it's not about Google, it's not about IBM, it's not about China, it's not about India, or it's not about United States or Netherlands or Australia and other things. However, that's how it is feeling. When you see we are having quantum supremacy, um, Google built quantum supremacy with 75 qubits, or China has invested $10 billion in qubit in trying to get their companies, countries, and other things. It's a race, and I believe that let's not race. Let's work like a team. I believe when we all these countries and companies work together, that's when this miracle is going to happen. The quantum to go to the and everybody is struggling um, to create a 200 300 qubit. Nobody has achieved beyond 70 qubits and keeping that to a high level. Uh, the goals are high. We want to do quantum internet, quantum computing to the computation power of 2 power 300 or more than that. And sometimes the power it's needed to understand a molecule to an uh, fullest level, it could be million qubits. So that means it is not going to happen if one country or one company tries to only do it. The way I believe one one country, one man could not have built this, right? So how the quantum computing uh, can come to the daily life is time compression. What I mean by time compression is what we are doing right now. At this particular point, this 1.5 hour of lecture has been delivered after 30 hours of learning, and you are going to be equivalent to my 30 hours. And if 30 people got benefited with this, they can build on to the next level. So this needs to happen with time compression, which is what we have done with International Space Station. So quantum initiative has to be done like International Space Station, where 20 countries were involved and they were doing their parts and they delivered their parts. And we assembled that on the space station, and everything is running smoothly. And this is again, that was the world's tallest building was civil engineering and architecture ingenuity, and this is aerospace um, and astronomers and all that. It's a different level of space industry, right? It's NASA and um, other country organizations. So let's not I believe we should not compete in quantum, but we should work together with quantum so we can achieve this much more faster. If not, it's going to be 50 years or 100 years. You never know. When every company has to, if they are not sharing the information, every country, if they are not sharing the quantum level of development, yes, there is concerns of cybersecurity and other things. However, there could be checks and balances. Those concerns could be easily addressed, that it doesn't fall in the hands of people where you don't want it to fall, right? We all know that concerns. So of course it can be taken care of like that. But the great thing is with this building, it is not like nuclear technology that it's going to be catastrophic. This one is, it's almost like crowdsourcing is needed right now for quantum, and that crowdsourcing it with multiple there are companies in Netherlands, Australia, and New Zealand, European countries, and all these countries have made tremendous amount of progress, along with the United States, of course. uh, and when we all join forces and we say, okay, what's the next level we want to achieve, what's the next level, that's when we are going to do this um, super computing, super quantum computing. If not, it's going to take many more years than we would like. So what can quantum computing solve? It's the clean energy solutions and why we need it, right? And it's like, we need clean energy, and we are seeing, we after this COVID has happened, only 4% of pollution has been reduced, but it is massive. Only that's it's easy to say 4% of pollution is reduced, but it is definitely millions of metric tons of carbon that has not gone into. But And quantum computing can yield good solutions, clean energy solutions that are very much needed. And it can resource efficient food production. And this with COVID is much more critical. There are predictions that food shortages can happen if there is going to be challenges in future. And if the food shortages are happening, that means we are not having good supply chain, right? So the supply chain has to be optimized, and the farming and so much stuff has to happen. So there's a vested interest for every country and every organization, every corporation, because we are countries later, companies later. We are people first, and we need food, and we have to help ourselves before we help uh, the country and this. So without food and with the shortage of food, it is going to be much more devastating versus collaborating on computing, quantum computing. So when we collaborate on quantum computing, we would be able to sustain a planet to a level of 9 billion people. And if we did not collaborate on quantum computing and helping with all this optimizations and resource productions, um, we would not be able to reach, we would not be able to sustain with the population that we have. So it is vitally important for countries to cooperate with each other and form a joint force to take to the next level. In medical side, it helps with genome sequencing and MRI and much more scanning. In financial industry, trending strategies, right? Portfolio optimization and many more financial information related stuff. A transaction has happened from a terrorist organization to somebody who was not in a terrorist organization, right? So we can easily track that and it's like, okay, what happened? So let's go to the source. And with cryptocurrency and with all of that artificial intelligence, machine learning, it's going to be much more easier to. And when with along with that, if we add quantum computing, it's going to be much more easier. There is going to be hardly I mean, the cash is going to be the challenge. If cash exchange happens, since it's not electronic, it's difficult to track. But maybe there will be a day where even cash can be trackable. So that being said, it's going to help quantum cryptography. It's going to come and it's going to be able to help with security. There will be a quantum key that is being distributed, right? And the quantum search that could help with new discoveries, calling for good healthcare that we all need, and then quantum simulations for financial optimization, as we talked about, and travel, self-driving cars, right, and secure quantum communication that can help. Uh, so better, efficient, better treatment, and improved stability for the whole world. So these are the resources. IBM Research Cryogenic Quantum Computer. Just search for IBM Quantum and they'll say this is the page you will land in, or this is the page quantum-IBM/quantum-computing, and you can go see that. And they have, if you are a developer or you wanted to learn a little bit more, they have something called Get Started with Quantum Experience. You don't have to be a developer. You can still be uh, non-developer, and they have given a UI UX as I have said earlier. So you can start with your experience and you can create something called quantum circuits. And with the quantum circuits, you can apply the gates and you can do all the simulations, and it will show calculations happening simultaneously, and it will show it right away with the results and programming. So that means you're already using a quantum computer. IBM has exposed this 5-bit, I think this is a 5-qubit quantum computer. So which you will see the power of it anyways. And Microsoft has quantum development kit, QDK, what they call. which is technological qubits that are available for this quantum computer. And it has, you can take the target machines, you can target the open source on GitHub, and you can just say quantum hardware. You want to use quantum hardware, you can run simulations. And they have a new language called Q Sharp for quantum coding. And there are libraries, there are examples. And then here's the one for GitHub. So this is the Microsoft one, github.com Microsoft/quantum, and you can take this, fork it, and go forward with. And there is quantum katas. Um, these katas from Juniper Jupyter Notebooks. So you can start looking into that as well. Just type in Google quantum katas and Jupyter. You can find it. So here I come to the session, and after this we'll open up for our own shameless self plugins, where it is, let's remove this word called shameless. It's just self plugin, not like this plugin. This information was quantum, was after 20-30 hours of reading and preparing all this material. I could deliver 1.5 hours of this session in depth, which will take a good amount of time for you to do it. So I have developed a course called 16 hours course called UI, UX, and accessibility, which is my primary area where I work day to day. I do not work in quantum computing. I just was an enthusiastic learner. And now I said, okay, let me teach what I've learned before I wanted to become an expert. And that's where my disclaimer came in. I I was not an expert, and I'm still not an expert yet. But here I am an expert in UI, UX, accessibility. There are in LinkedIn, somebody asked somebody who is an accessibility expert, and they were few of my LinkedIn colleagues pointed. Harish is the person. I think Kelly is on the line, and their team wanted to reach out to me on accessibility. So I'm a legally blind person at the same time. I can still, that's one reason I care really about accessibility, where people need to be able to do that. And UI and UX. So nobody needs, so for this course, it's a 16 years of UI, UX, and accessibility. I mean, it's a 16 years of front-end experience that I'm compressing in 16 hours of intensive course. Like this, I know this hour was intensive, but that was the idea of it, to learn intensive information and decompress, and then go back and learn it. So that course is going to, they have to listen, learn, leverage, and where they have to practice some real life projects, and then they can level up into this. So it's a fast track course. Somebody who has no experience, but they're interested in finding jobs, or they are trying to, um, they are they don't know where to settle. They can have a 1 hour free meeting with me. I can mentor them, and then I can guide them, even if it's college students or just finished up. They are not having a clue. They don't want to go programming. This doesn't have to do anything to do with programming. Everything is design concepts and fundamentals and advanced concepts that they can use to uh, become a big designer themselves. So that being said, the course is at uiux.floralms.com, uiux.floralms.com, and the course is listed over here. There's a 32-minute free video that is published. I published a 15-minute free video as well on LinkedIn, but this is over there if they want to look more before they start buying the course. And then before you buy, and this model doesn't exist in the industry where anybody sells a course with each module by module. I do not want to play any gimmicks with people where 100% money back guarantee, where I charge them high amount, and then not even where they drop the course in middle, they lost that amount. I do not like that, because whenever I did that, I felt so bad that I'm not going to do this. I'm going to just keep module, you can only purchase one module, and if you don't like the first module, don't even purchase next module. So it is 8 different payments. So that means in an investment, you just have to invest $125 to figure out if you want to go in this field or not. And then after doing a free trial run of 35 minutes or 30 minutes, then you say, I want to learn it, I want to go. Then 2 hours, each is 2 hour session, 8 sessions. So, and you can go into the details what it is you're going to learn in, let's say, the class 4 of UI UX accessibility, what is going to be there. I give that details in description. And these are the people who have taken my course, and there are a few more I didn't have enough space to put in. They loved, Yessie, she's working with me on a project, uh, like a fun project, real life startup kind of fun project. There is another person, and they have started from knowing a little bit of it, but now they are becoming pros, professional UX designers. So that's what is happening with this. So that's my shameless self plugin, and classical and quantum computing. We are going to be using both in future. So let's get ready to start thinking about it and some resources. So any questions, and then we will do questions and answers. And also feel free to express your area and something that you're working on and you want to share with others, and you would like to um, interact with others and do a little bit of networking. Feel free to do that. Please unmute yourself and then go ahead and talk. And thanks all for attending this session. This has been my one of my favorite topics that I have been wanting to talk for a long time. And it became true with Flo's meetup over here. Go.
Awesome. Well, thank you all for coming to the session. Like I said, there might have not been people on the line earlier, but we do these meetups usually once a month, or maybe sometimes twice a month. But again, this is one of the more technical topics. We do technical and design, just pretty much innovation. So some of the next topics that we're thinking about doing are design for accessibility, as well as search engine optimization. So once we do something a little bit more technical heavy, we always want to kind of mix it around. So I want to thank you all for coming, and all the newbies that are new to front end creatives. And we definitely have more talks in the future.
Yeah. Anybody wants to socialize? We have like 10 more minutes of the time available. So
Harish, this is Kelly. I have a question for you about
yes.
the quantum computing. What resources, like, what do you think I can do to learn more about applying this to UX and specifically human-centered design?
That's a great question. I think this is where if you look at IBM get started with quantum experience. And here you can start with this one where the quantum circuits and development of this. So once you start, their UX is okay, but once you understand what quantum circuit is, what the gates needs to be applied, and how the calculations and simulations are going to be performed. So there is going to be apps that can be developed, and these apps are going to be incredibly powerful. However, that's going to cost because every qubit is going to be, if this is for plug and play for people to learn, but once you start using this on a commercial basis, um, I don't know if they're production qubits, right? So there's going to be a lot of information at this particular point. I think to understand a sector, let's say if you're in the healthcare sector or supply chain sector or finance sector, the way to look at quantum computing is what the portfolio optimization algorithms are doing right now, and what are the current technology in the scape, and how a quantum computer can tell you upfront, like, hey, you need to sell this because this is reaching this low level. You need to upgrade it. I was like looking at 10 different variables, looking at the sources like Facebook, YouTube, or internet, press, any media. So if like 2 or 3 days ago something is happened, and it can correlate that information saying that, okay, looks like with all the information on the internet, looks like Tesla is going to come up with a new car that's going to do XYZ. So it's better for you to go ahead and buy Tesla. So all that information, how it has processed, some kind of application should be there, some kind of an experience. So right now, what you see over here is going to be more technical, how a circuit is, it's more like this. But once you start imagining with an industry where in your industry, if it applies, if for quantum, then you can start creating applications and user experiences where the users will not know that they are on quantum, because it could be quantum cloud computing, right? So instead of classical route, they probably will expose these quantum computers on the cloud itself, right? Like how they are doing over here. This is on the cloud. So, and there will be a commercial licensing and the aspects of it. So this is futuristic, what we are speaking, maybe 5 years down the road, I do not know, but I'm just guessing. However, if the companies collaborate with each other and they come up with much more big, it's not even like a data center, it's going to be, um, data centers are lots of servers and lots of things, and this one would not even need that much. So it's going to be a, one of the floors in Microsoft buildings itself. So uh, the short answer is understanding your areas of sectors, especially farming or technology or finance or medical, and then applying what is the most challenging computational problem we are solving. Let's say genome is one of the most challenging. So having an app or applications and experience for the genome, how a user can quickly get sequenced with the genome and everything, something like that. Does that make sense?
Yes, that makes complete sense. Thank you.
You're welcome.
That thank you for putting it into more of a like application for me. My brain didn't
No problem.
understand it.
Perfect. Sounds great. Any other questions, anybody? So if not, I think as there is a saying goes in America, right? There's no free meal in America. So this information, the only thing I request is if you can put any comments on the LinkedIn or anything, that's fine. And then more importantly is the course that I would like to start venturing out, because this is one of my passions, to sell the course and be able to teach and help people grow. So yeah, if you can, if you or anybody and anybody else in your field is ready to become a UX designer, or they don't know their job, or they lost a job and they are still figuring out, then they can definitely approach me, and I could give them at least a free hour consultation, and after that there is need, they would like to go and invest their time. I could say my designers are doing like excellent professionals, and they have had almost like 120 hours of 16 hours of intensive training, and then their real life projects they are working on for like X number of hours. So now within 120 hours, you could be employable, or somebody could be employable. Um, Starting with, so a $1,000 course taking you to that level is going to be, it's very challenging. You have to either spend 50 grand going to the bachelor's degree, master's degree, or whatever it is. Uh, but there is a prediction by Tony Robbins and other things, and I think they are going out of predictions from some of the internet and some of the gurus' predictions that self-education industry is going to be much more higher. It's currently at $400 million per day. It's going to go to $1 billion per day. So that means, as you guys already seen, education is going to come online, and people are going to create more courses and train other people without having to go spend 50 grand, where you can learn that in through an expert, and then you can be of employable skill set. So yeah, that's the ask and the request for you guys to help. If anybody let them know about this. Yep. Anybody else want to share anything? Flo or anybody on the line? Kunal or
Yeah, Harish, this is Chris Wagner. I just want to tell you thank you very much for putting this on. When I saw the invite come across about quantum computing, it sounded like something out of a physics lab or something, and I knew nothing about it, so I appreciate the overview.
oh,
And
thank you
Flo,
so
thank you very much for coordinating this.
Yeah, no problem. No problem.
Yeah, appreciate it too. Thanks, Chris. Appreciate your sharing the information. Okay. So, anybody else going once, twice, and thrice? So, if nobody else, no information, then have a wonderful week and weekend. Thank you so much for attending.
Awesome. Thank you all.
Thank you.
You're welcome.